This video covers the navigation page of the ACEP Premium Access portal. The navigation page interface consists of a mission progress slider and 5 display panels. These panels cover transit kinematics, spatial orientation and deviation, relativistic time behavior, numerical speed and distance readouts, and positioning system status. Together, they form a unified view of ACEP's navigation state along the interstellar trajectory. The Mission Progress slider provides a longitudinal representation of ACEP's transit from Earth to Proxima b. It displays mission completion simultaneously as true distance traveled and relativistically contracted apparent distance, both updated continuously from the active navigation solution. The solid bar represents true distance along the trajectory, while the dashed overlay represents the length contracted distance in the spacecraft frame. A movable ship marker indicates the current mission position, with a numeric percentage showing total route completion. Tick marks indicate major physical and operational boundaries, including the heliopause, the Oort cloud region with elevated debris encounter probability, abort feasibility limits, and the mission midpoint. The IABT, or indifference abort threshold, marks the last point for a fully propelled return. Beyond it, return requires a non-propulsive coasting phase to conserve fuel, with rapidly increasing return duration. The Transit Data Panel displays the time evolution of ACEP's interstellar trajectory as a set of overlaid kinematic and navigation curves indexed by mission day. The graph simultaneously shows true and apparent speed, true and apparent distance traveled, true and apparent remaining distance, accumulated position error, and abort return timing. Speed curves are plotted as fractions of light speed, with solid lines representing true values and dashed lines representing apparent values in the ship frame. Distance curves are plotted in astronomical units, allowing direct comparison between traveled and remaining range under relativistic length contraction. Position error is shown as a cumulative deviation estimate in kilometers. Abort to Earth time and required coasting duration visualize return feasibility at each mission epoch. A movable vertical marker allows inspection of historical or current states, with a data box reporting exact numerical values for the selected mission day. Small orange markers on the true distance traveled curve indicate MADS events, marking individual space debris detections and neutralizations. The Orientation and Deviation panel displays ships' instantaneous pointing, attitude, and cross-track deviation in a fixed astronomical reference centered on Proxima Centauri. The background can be switched between synthetic star catalogs and multiple physically derived sky maps, including optical, infrared, X-ray, gamma ray, and molecular gas distributions, all pre-projected in the same celestial geometry. Field of view is selectable between wide, medium, and narrow angles, and the display grid can be toggled between celestial, galactic, and ecliptic coordinate systems to place the spacecraft orientation in different astrophysical frames. Star identifiers, reference grids, and the galactic plane indicator provide absolute spatial context for interpretation of attitude and drift. The spacecraft's forward trajectory vector remains fixed at the display center, while a live attitude symbol reports yaw, pitch, and roll relative to the trajectory and the galactic plane. Numeric readouts provide angular values with arc-second level precision. A magenta deviation frame, dynamic crosshairs, and scalar error readouts visualize the current cross-track displacement and navigation uncertainty envelope in kilometers. Together, these elements provide a precise visual correlation between celestial orientation, inertial attitude, and accumulated trajectory deviation during relativistic cruise. The time dilation panel visualizes the relativistic divergence between the ship's proper time and Earth frame coordinate time. The graph plots mission time on the horizontal axis and shows as continuous curves true velocity as a fraction of light speed, accumulated Earth ship time offset, the instantaneous rate of time divergence, and the relative clock rate of the spacecraft. As velocity approaches relativistic regimes, the Lorentz factor increases nonlinearly, causing onboard clocks to slow relative to Earth clocks. This effect is shown both cumulatively as the growing time offset delta t and instantaneously as the rate of change of that offset, describing how much faster Earth time advances compared to ship time at the current velocity. The numeric panel reports the current true speed, Lorentz gamma factor, clock slowdown percentage, elapsed proper time, elapsed Earth time, remaining proper time to arrival, and the projected final Earth ship time difference at arrival. Together, these values quantify how relativistic time dilation compresses the subjective duration of the journey for the spacecraft relative to observers remaining in the solar system. The speed and distance panel presents a numerical snapshot of ACEP's translational state along the trajectory, grouped by reference frame and physical meaning. Values are organized into true Earth frame quantities and apparent ship frame quantities, allowing direct comparison of relativistic effects. True speed is reported simultaneously as a fraction of light speed and in multiple linear units, including light hours per hour, astronomical units per second an hour, lunar distances per second an hour, Earth circumferences per second, and kilometers per second. Distance traveled and distance remaining are shown in light years, light hours, astronomical units, and kilometers, representing the actual coordinate distance covered and remaining along the Earth Proxima b trajectory. The apparent speed and apparent remaining distance sections report the corresponding ship frame values, reflecting relativistic time dilation and length contraction. The Positioning Systems panel displays the current status and performance of all onboard navigation subsystems and their fused solution. A historical error plot shows positional uncertainty in kilometers over selectable timespans, allowing comparison of short-term stability and long-term drift. The Inertial Navigation System section reports the state of individual IMU units, their accumulated drift, and the combined inertial error estimate. Active units are shown with per-unit displacement and angular bias, while standby units are held in reserve for fault tolerance. The Star Tracker section reports optical attitude solutions derived from stellar pattern matching. It lists the current pointing vector, angular error, number of matched stars, and the galactic regions used for reference, together with the cumulative optical navigation error. The XNav section presents pulsar-based positioning data, including the tracked pulsars, their rotation periods, timing precision, solution status, and the resulting positional uncertainty. This system provides an absolute deep space reference independent of optical or inertial methods. The ORI section displays the fused navigation solution, combining inertial, optical, and pulsar inputs into a single best estimate position. This solution is computed by ORI, the ship's primary autonomous operations system, which continuously performs multi-sensor fusion, forward prediction, internal consistency checks, and cross-core consensus across two independent processing instances before accepting any navigation state. Coordinates are reported simultaneously in celestial, ecliptic, and galactic frames, together with the current overall position error and tracking status. Together, the navigation page provides a complete, time-resolved representation of ACEP's position, motion, orientation, relativistic state, and navigation confidence throughout interstellar flight.